Okay, so this is the second in the series of lectures. And as you all know, the lectures are posted on the web. And there was something I missed from the first in the series. I just want to finish up. When you have grand unified theories in 4 dimensions, there are some problems which I'll get to in a moment. But there are some nice features. If you write down a complete theory for the fermionic sector of the theory, which gives masses to quarks and leptons, then you can get quite predictive theories. In fact, in a paper with Dermashek, we wrote down an SO10 gut, and then we included a family symmetry. And the family symmetry was a D3 family symmetry where the first 2 families were a doublet under D3. D3 is a discrete non-abelian subgroup of SU2. It's also equivalent to S3, the group of permutations. And we wrote down a theory which looks something like this. Of course, we wrote down the superpotential, and this is just the Feynman diagrams that you get for the effective fermion mass operators. This is a Frogot-Nielsen type theory. These chi fields are doublets under the D3, and they get large mass of order or larger than the gut scale. In particular, it's larger than the scale of these VEVs. And so when you integrate out this chi field, you get effective higher dimensional operators. I point this out here because when you construct string models, in particular heterotic string models, the fermion mass operators will be effective higher dimensional operators. The D3 symmetry is carried also by these flavon fields, phi A and phi tilde, which are doublets under the D3 family symmetry. And until you break this D3 family symmetry, the only diagram you have is the 3rd generation Yukawa coupling, which gives lambda top equals lambda bottom equals lambda tau is equal to lambda nu sub tau. Once you break this symmetry, you generate these other terms in the Yukawa matrices. And if you look at the papers that we wrote down, at least in the notes, you'll see that we wrote down all the possible terms that you get from integrating out the chi bar, giving arbitrary VEVs, particular VEVs, to these flavon fields and to this field A. The 10-dimensional representation here is the Higgs representation. It contains the color triplet Higgses and contains the Higgs doublets. We included in this theory a doublet-triplet splitting mechanism, which is natural Dimopoulos-Wilczek mechanism, which is natural in SO10. And you write down the complete theory. The complete theory, including SUSY breaking sector of the theory, including all the Yukawa terms, all the terms in the Yukawa matrices, had 24 parameters. That's in fact fewer than the number of parameters in the standard model. That's fewer, even much fewer than the number of parameters in the minimal supersymmetric standard model. When I say it's fewer than the number of parameters in the standard model, you may think that there's 24 parameters in the there are 18 parameters in the standard model, but that doesn't include neutrino masses and mixing angles. When you include neutrino masses and mixing angles, there are 27 parameters in the standard model. And this model has 24 parameters, including the parameters for neutrino masses and mixing angles. So we also fit neutrino data. I pointed it out because it's a predictive theory. We did a global chi-squared analysis on this theory. We take the parameters at the gut scale, and we renormalize down to low energies. We calculate all the precision electroweak data, but included in precision electroweak data now is the top quark mass, the bottom quark mass, the tau mass, the electron mass, the muon mass, et cetera, et cetera, et cetera. All the CKM mixing angles, the neutrino masses, and mixing angles. And we get lots of predictions. I just want to point out, one of the first predictions that you get is coming from this boundary condition, Yukawa unification. If you have Yukawa unification at the gut scale, there's only a small set of parameters that you can put in. Well, first of all, you have SO10. So the scalar masses have a mass M16 because under SO10, they transform as a spinor representation of SO10. The squarks and leptons transform as a spinor representation of SO10. And so they have to get the same mass M16. You can give different masses to the 3rd family of squarks and leptons, but you have to give the same mass to the first 2 families because they transform as a doublet under D3 family symmetry. So we give a universal mass M16, an A parameter, which is coupling to, if you just study this sector of the theory, there's a universal A parameter there. There's a mass term for the Higgses, which are in a 10. And it turns out that you have to split the two Higgs. Well, there's other parameters. I'm not going to write down all the parameters. You can look at the paper. You're forced, in order to fit the top, bottom, and tau masses, you're forced to a particular region of soft-SUSY breaking parameter space. And the region of soft-SUSY breaking parameter space that you're forced to is where this mass term, the scalar mass, is typically a factor of 10 larger than the gaugino mass, the gaugino masses m1/2 or the mu term. So you're in that region of parameter space. You're also forced to a region of parameter space where A0 is approximately minus twice M16, and M10 is bigger than M16. It turns out that in order to fit the data by now, we have to have large values of M16, and I'm talking about recent analysis of this, which was done by Boras and his collaborators, which showed that M16 had to be fairly large, around 10 TeV. In order to fit the data, I just want to point out the following fact. When you have lambda top equals lambda bottom equals lambda tau is equal to lambda nu sub tau, all those Eucalor couplings for the third family are large, of order 0.7 at the gut scale. They tend to drive scalar masses lighter, whereas gauge couplings by a renormalization group running drive scalar masses lower at low energies. So the first two families of quarks and leptons at low energies have a mass of around whatever you choose for M16. However, the third family of quarks and leptons has a mass which is significantly lighter than M16, typically around a factor of 5 smaller. And so you're left with, if you choose M16 5 TeV, you have your third generation quarks and leptons lighter than a TeV. Gaugino masses are typically in the hundreds of GeV range. The gluino, 600 GeV, something around there. The charginos, neutralinos, et cetera, could be 100 GeV or so. The nice prediction that you get out of this is you always get the light Higgs mass of around 120 GeV. It's a prediction of the theory. It may or may not be correct, but we'll find out. You can also write down the soft SUSY breaking. Since you know what the soft SUSY breaking parameters are approximately, you don't know the overall scale, but you know the ratios, you get predictions for quark and lepton masses and gaugino masses. And I didn't write them down, but typically, in order to fit all the data, the CP-odd Higgs is degenerate with the charged Higgs, which is degenerate with the heavy Higgs, which is around 600 GeV or greater. And that's in order to fit a process called B sub S decay into mu plus mu minus. A B meson with a strange quark in it is B sub S. It can decay via flavor violating processes in the large tangent beta regime. I should mention here that in order to fit the top quark mass, you're talking about tangent beta of order 50. So this is the large tangent beta regime. It's in order to fit the ratio of the top to bottom quark mass. It's not coming from the ratio of lambda top to lambda bottom because that's of order 1. So it has to come from the ratio of the two Higgs vevs, which is a tangent beta. Anyway, in order to fit that, B sub S process goes to mu plus mu minus, is enhanced by a factor of tangent beta to the power 6. As a result, you're sensitive, and people at CDF and D0 at Fermilab are looking for this process. They've never seen it, but the branching ratio for this process should be at least an order of magnitude larger than that of the standard model. And in fact, they're getting down to the regime where you should see it, or you start excluding this large tangent beta regime. So there's lots of predictions that come out of this theory. The point is that if you have a theory, which is a grand unified theory, probably in addition, you have to add family symmetries in order to make it predictive. But once you get a predictive theory, you get lots of predictions. And in order to test these theories, you're going to have to test the correlations between all of these predictions. So that's the bottom line. So that's what I want to leave you about 4D SUSY guts. And now, after I give you that, let me tell you what the problems are with 4D SUSY guts. The problems are, and I'm not going to write down the superpotentials that you need, but you have to do gut symmetry breaking. In order to do gut symmetry breaking, you have to have a Higgs sector of the theory at the gut scale, which spontaneously breaks the SO10 or the SU5 down to the standard model. Minimal SU5 is ruled out. That had the simplest SU5 breaking sector of the theory. That required at least an adjoint. When you get to SU5 with natural doublet triplet splitting, you need representations like this of SU5, 75-dimensional representation, 50, 50 bar, and it starts looking horrendous when you write down the superpotential to do gut symmetry breaking and then do doublet triplet splitting. So the other problem is doublet triplet splitting. The Higgs color triplets have to be much heavier than the doublets. It's not that you can't do it, but when you do it, it doesn't look very pretty. It's not something you want to write home to your parents and say, look, I came up with this great theory. And in fact, I can say that because I've written down some of these theories. They don't look pretty. They work. They're existence theorems. But this is a problem of these theories in my mind. And so what you'd like to do is try to solve these problems. And the final problem is the following, that you can write these things down. They're complicated. And from my point of view, I'd like to eventually fit this theory that I write down into more fundamental theory, such as string theory. And I can't see any way that anything that we've written down can come out of a string. Okay? So there's a problem in my thinking, and so I want to solve that problem today. So this way to solve this problem is to discuss orbifold guts. The possibility that your grand unified theory is a grand unified theory in 5 dimensions or 6 dimensions, but when you get down to 4 dimensions, you've broken the unification symmetry, the gut symmetry, down to the standard model or something larger. And you've done doublet triplet splitting also by this orbifolding. Okay, so we want to do orbifolding of 5D orbifold gauge theories today. And then the next week, I'll show you how you can sort of take these 5D gauge field theories, which have a problem in themselves in the fact that they are non-renormalizable theories. They're effective theories because you're in 5 dimensions and you get divergences which increase to every Feynman diagram you're going to write down is going to have higher and higher divergences. Okay, so it's a effective field theory, which in order to calculate, you have to put an effective cutoff into the theory. To try to solve that problem in these theories, we're going to go to string theory. And we're going to embed our orbifold guts with an ultraviolet completion in string theory, and we'll do that next week. Okay, any questions? Okay, so let me start the picture of orbifold guts. And I'm going to start out with, oops, where did I put it? I'm going to start out by discussing guts on a circle. Just to get into the notation. So let's imagine that we have a theory which is SO3 gauge theory, and I'm just going to discuss the gauge sector of the theory. And it's going to be defined on a circle which is Minkowski space. What I mean by a circle is Minkowski space cross a circle. So it's 5-dimensional. The gauge fields in this theory we'll call AM. Index M goes from 0, 1, 2, 3, and then the last one is 5. And it's a function of coordinates x mu, which are the 4-dimensional coordinates, and the 5th dimension I'll call y. And y goes from 0 to 2 pi r. I'll write this in terms of component fields AMA of x and y times generators TA. So this is a 3x3 matrix in the adjoint representation of SO3. The field strength for this theory, FMN, is also a function of x and y. Also be written as a matrix. Okay, so that defines the field strength for the theory, and the Lagrangian finally is given by the following. It's a 5-dimensional Lagrangian. We'll write it as minus 1 over 2g 5 squared times k trace of fmn squared. Why is k there? K is there because I haven't told you how I normalize these generators. And so in general, they'll be normalized like that with a constant k. The theory is invariant under gauge transformations. The gauge transformations are the following. Where U are the representations of SO3. And could be written in that form. Okay, so let's try to get a little bit of familiarity with this theory. Let's, for example, look at the case when let's set, or take this circle S1 to be infinitesimally small and have no fields depend on that fifth direction. So let's imagine that, in fact, let's imagine that d5 a mu is equal to 0. That's all I need. And study this theory in that limit. And we'll come back to the more general theory later. In that case, you can work out what f mu 5 is. And f mu 5 is d mu a5. There's no minus d5 a mu term because of this condition. The next term is I a mu commutator with a5. And the nice thing about that is that you should recognize that because that is just equal to the covariant derivative of an adjoint field. What's the covariant derivative of an adjoint field? Under any gauge symmetry, it can be written like this, where the commutator is a representation of the matrices of how this gauge field transforms, or how this adjoint field transforms under the SO3. So this is an identity. Any questions? Clear? Good. Okay, we can define in this limit, we can define a new field phi tilde to be equal to A5 And why am I doing this? Well, first of all, let me point out that the coupling constant here has dimensions. G5 has dimensions. Okay? This is a 5-dimensional Lagrangian. The gauge field has mass dimension 1 still, even in 5 dimensions. So this has mass dimension 4. And so 1 over G5 squared has to have mass dimension m to the power 1. Okay? This quantity here is dimensionless ratio, and I'm just scaling out this dimensionless ratio because we're going to eventually integrate over the 5th dimension. We'll define this quantity here as A5, well, it's just A5 over G, where G is the dimensionless coupling constant. This is dimensionless because this quantity is equivalent to square root of 2 pi r times a mass term under the square root, so it's a dimensionless quantity, and we'll define that. We're using this to define G, the gauge coupling of the effective 4-dimensional field theory. Okay? So G is the dimensionless gauge coupling. And now, rewriting the Lagrangian L5, it can be rewritten like this. It's 1 over 2 pi r. That factors out. There's a minus 1 over 4 g squared k. where G is the dimensionless effective 4D gauge coupling constant, trace F mu nu, F mu nu. These are the four-dimensional field strength squared. And so this is the Lagrangian for a four-dimensional field theory. In particular, when we integrate this over the y direction, y from 0 to 2 pi r, this will go away if these fields are independent of y. And then we have the second term, which is 1 over 2k trace of covariant derivative phi tilde and so in this limit, this theory reduces to that of a four-dimensional gauge theory and a four-dimensional scalar field in the adjoint representation of the gauge group. Okay? So out of the 5D theory, when we compactify it, or dimensional reduction as John called it, we get a 4D gauge group theory and a scalar in the adjoint representation of the gauge group. Oops. Okay, more generally, in general, AM is a function of y. So in general, AM will be a function of x and y, and can be written in terms of a Fourier decomposition. Since the y degree of freedom is a periodic degree of freedom, this has to be a periodic function of y, and you can rewrite it as sum on modes of the following form: AM of x times cosine ny divided by r plus bm n of x cosine ny divided by r. So this is the complete Fourier expansion of this periodic function of y in terms of its modes. And then you can realize, since the kinetic term in a particular gauge, you can work out what the field equations are for the gauge field AM, and the field equations for AM will be proportional to the five-dimensional D'Alembert, which will give you a d mu term plus a dy term acting on AM, and the dy term acting on AM will give you a effective mass squared for this gauge field in four dimensions, where the mass term m sub n squared is equal to n squared over r squared. So only the n equal to 0 mode is massless. All the other modes give you the Kaluza-Klein excitations of this 5D gauge field. Okay? So we have Kaluza-Klein excitations when we go to 5 dimensions of all of these infinite tower of scalar modes. Okay, before I get to guts, before I get to guts, let me discuss fermions in 5 dimensions. And then I'll orbifold this after I discuss fermions. Fermions. In 5 or 6 dimensions, a Dirac, or smallest dimensional fermion, is 4-dimensional. So fermions are 4-component spinors in 5 or 6 dimensions, and they satisfy the wave equation which is given by this, where these are the 4x4 gamma matrices which satisfy the Dirac algebra in 4 dimensions. In 5 dimensions, the algebra they satisfy is given by this. where G is a matrix in my notation, time component and 4 spatial components minus, 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 minus. Is there a question? Okay.
Yes. This condition, the question 5 n is equal to 0.
That was just, I just chose that as a possibility. It's not a gauge condition or anything.
Yes. So how is it consistent with this expansion here?
It's not. It's not. So this is the general case. In general, this is what you have. That was just a particular example to show how you get these massless adjoints, effective 4D adjoints, coming out of the gauge theory, right? I'm starting to think ahead, but they're scalars in the adjoint representation of the group in the effective 4D theory, okay? I was wondering, somebody bring me down bigger pieces of chalk? I could start using these other chalks, but they don't erase. Is there? Yeah, that's also the one that doesn't erase. I was looking for the square ones, but anyway, we'll see. Okay, this Dirac spinner, or this 4x4 matrix, 4-component spinner in 5 dimensions, will break up into 2 Weyl spinners when we look at 4 dimensions. So we can rewrite this as a containing 2 4-dimensional 2 Weyl spinners. Just like we wrote down in 4 dimensions, a Dirac spinner is written in terms of 2 Weyl spinners. The difference here is that in 5 dimensions, this is the smallest dimension for a spinner. It's 4-component spinner. But when we break it down to 4 dimensions, we'll get 2 Weyl spinners in 4 dimensions. Do you have? Oh, those are like the square ones? Okay, we'll try. Thank you. And if we write down the gauge theory coupling to fermions here, we're going to find out since the fermion is 4-dimensional, the gauge fields have to couple both to the psi1 Weyl spinner and the psi2 Weyl spinner. In other words, it has to couple to both the left-handed and right-handed degrees of freedom of this 4-component spinner. Any gauge field that you write down in a 5D theory will couple to both the psi left and the psi right in the same way, in the same representation of the group. That's why a 5D theory is a vector-like gauge theory. It's not a chiral gauge theory, because you cannot couple to the left and right modes differently, okay, like you have to do in the standard model. So you don't like this fact that you have a vector-like theory because it doesn't fit low-energy data. And so you want to break that vector symmetry and get down to a chiral theory. And the first reason we might want to do orbifolding is because we can use orbifolding to break this chirality of the theory. Let's define the gamma 5 matrix here in a particular representation where I've diagonalized gamma 5. Let's choose it to be that. That's a 2-component 2x2 matrix, identity matrix up here, and a 2x2 identity matrix down there. Okay, so it's a chiral basis for gamma 5. And if we imagine, well, first of all, if we don't do anything, then these fields are also periodic under y goes to y plus 2 pi r. And so they also have an expansion, and I'll write down that expansion like this. Hopefully, okay, so we have the expansion for the left and right movers are like this in general. But let's imagine that we have a symmetry under parity. This theory does have a symmetry under parity, and parity will define as taking the psi field x, mu, and y and transforming it to psi of x, mu, and minus y, which is equal to some operation, which I'll call gamma 5, on psi of x, mu, and y. Let's define our operation like this, such that under parity, we don't get back to psi x mu of y, we get to back by a gamma 5 operation. That would be an orbifolding. We would be projecting out half of the degrees of freedom if we required the fields to satisfy this, instead of just psi of x mu. Well, let's require the fields to satisfy this. Then what does that do for us? If we require this as a boundary condition on our fields at y equal to 0, then the left modes, with this definition of gamma 5, the left modes are odd under, oh no. That's what I want. The left modes are even under this operation, and so the left modes, if we require that as a boundary condition, as an orbifolding boundary conditions, the left modes are proportional to cosine ny over r, and the right modes, the only ones which satisfy that condition would be proportional to sine ny over r. So if we require this orbifolding boundary condition, we require fields to satisfy this condition, where there's this parity operation here associated, and the fields have a parity which differs for the left movers and the left chiral modes and the right chiral modes, then we split the degrees of freedom. Only the psi left would have a 0 mass mode, and the psi right would have massive modes only. Okay, we get rid of half of the degrees of freedom, and by doing this orbifolding, we get down to a theory which has a chiral gauge theory for massless degrees of freedom. Okay, so the first reason we want to do orbifolding when we work with higher dimensional theories is to be able to get a chiral gauge theory. Questions? Okay. Now, I realize that I sort of jumped ahead with defining orbifolding before I defined orbifolding, but let me do that now.
Professor Raby?
Yeah.
What did you say was the dimension of psi? Is that 5?
Psi is a 4-component Dirac spinner.
Okay.
So it's a 4-component vector. Okay. So we're going to define orbifolding now in more carefully. Okay? First of all, let's take our circle and define the circle in the following way. Let's take the real line and mod out by a translation. So here would be a picture of the real line. Here's 0, here's pi r, here's minus pi r, minus 2 pi r, and it goes out to infinity on both sides. So it's just the real line. And we'll mod out by a translation group, T. And the operation of the translation, T acting on y takes us to y plus 2 pi r. Okay? If we mod out by that, then anything outside of this domain here, from minus pi to plus pi, can be mapped back into the central domain by a translation. Okay? So we've reduced the fundamental domain of this theory to being a circle where this point and this point has been identified by the translation operation. Okay, so we've defined a circle by this space group translation operation. Now I want to define a parity operation which takes y to minus y, assuming the theory that I write down is invariant. Well, we can make it invariant into translations easily. The theories will be typically invariant under translations, and then we mod out by this translation group. If the theory is also invariant under a parity operation, we can mod out by a parity operation. It's a symmetry of the theory. Okay? And the parity operation takes y, any point over here, to any point over here. Okay? So we start out with a circle after doing this, and the parity operation takes the point, any point on this side, which is y between 0 and pi r, and maps it to a point on this side between 0 and minus pi r. Okay? And so we've now reduced the circle into, by identifying things under that parity operation, we've reduced the circle to a line segment, which goes from 0 to pi r. Okay? And this line segment, defining our theory on this line segment, is an orbifold. It's an orbifold because these points, 0 and pi r, are fixed points of the operation, of the parity operation. 0 doesn't go anywhere under the parity operation. Pi r doesn't go anywhere under the parity operation. So this symmetry operation, this Z2 parity operation, Z2 parity operation has fixed points. It's not what they say is freely acting on the circle. Okay, so we've taken our field theory that we're going to define on this space and mod it out now. So this is S1. We're going to mod out S1 by this Z2 parity operation. We get an orbifold. Okay? And we want to define our degrees of freedom, our modes, expansion, etc., consistent with the parity operations, the translation and parity operations. I should point out that if I take a point here, take an arbitrary point on this side of 0, between 0 and minus pi r, and do a translation, what happens to that point? Under a translation, that gets translated over to here. Okay? If I take that point now and do a parity operation on it, it gets translated over to here under the parity operation. If I now do another translation on the resulting point by 2 pi r, I go from here to here. By another translation. The net effect of doing a translation, well, I do it in this order, but the net effect of doing a translation followed by a parity operation followed by a translation is equivalent to a parity operation. And so there's an identity here that says okay? And so there's a relationship between these things. Okay, let me represent now these parity operations on fields, okay? We can take the parity operation acting on a field, say phi of x mu and y. We're actually going to apply this to our SO3 gauge theory. We'll come back to the SO3 gauge theory. So let's think of phi as being a representation of SO3 for the moment, okay? In some representation of SO3. And the parity operation does the following. It takes the field phi of x mu and y into the field phi of x mu minus y. And we can think of having an intrinsic parity as well, like we did for the fermions, and say that up to an intrinsic parity, it comes back to the same field, where since p squared is equal to the identity, we'll take p squared, the representation, also be equal to the identity. So p, the eigenvalue p here for the intrinsic parity, can either be plus or minus 1. Just like we chose for the fermion before, we had plus or minus 1 for the different left or right movers. Similarly, for the translations, acting on phi x mu and y, this will take us into phi of x mu and y plus 2 pi r. Okay, and we want to relate this back. Remember, we're going to start out with periodic functions. Typically, you would start out with periodic functions. But since this is a gauge theory, we can start out, we have periodic functions which come back to the same function. But they can come back to the same function up to a finite gauge transformation. And so let's put in the possibility of having a finite gauge transformation multiplying this field. That finite gauge transformation can quite generally be written in the following form as the exponential of I times the integral, say, A5, the component in the fifth direction of the gauge field, integrated dy. If I take it in, say, the third direction or the first direction, A5 in those directions will commute with itself, and I don't have to do any path ordering here. But in general, you might have to do path ordering. Okay, so T can be represented as a what's called a so-called Wilson line. So by a translation, we come back to the original. Instead of just being purely periodic, they're periodic up to the possibility of coming back with a phase. Okay? And that phase, we want it to be satisfy also t squared equal to 1. Okay? That would be what is called a discrete Wilson line. And I'm cutting short some discussion of all of this. And if you want to see more discussion on this, there are two nice papers you can look at. I think I referenced one of them in my notes, which is a paper by myself, Dermashek, and Nandi. But there was another previous paper by Hall and Moriyama and somebody else, I can't remember, where they discussed the relationship between these phases here under translations and Wilson lines. Okay, so that's discussed in complete detail in those notes. So if you're interested in more detail on that, I suggest you look at there. So we'll take T. First of all, T is an element of SO3, gauge group, and we're choosing it to satisfy T squared equal to 1. So it's sort of like a parity operation. It's a what's so-called discrete Wilson line. Okay, under that operation, what did I do? I lost the blackboard. Under that operation, we have this condition. Tau p tau is equal to parity operation. And the representation of p and tau on the field is p and t. And so we have the condition that pt squared is equal to 1. Now, I've assumed that I can diagonalize both the parity operation and the translation operation in the same basis. Okay, basically I've assumed that p and t commute, so you can check now that pt squared in fact is equal to 1. And with this quantity here, pt, we can define a new parity operation, which is just given by the product of p times t. And you can ask, what does the product of p times t do? Can you see that? If you take the product of p times t, you do a translation first and then a parity operation. I'm not going to try to reproduce it there now. But if you do the product of p times t, acting on the coordinate y, you should be able to convince yourself that that gives you y minus y plus 2 pi r. So the parity operation p prime, or capital P curly p prime, is equivalent to saying y goes to minus y plus 2 pi r, which is equivalent to reflecting around the point pi r. Okay? It's just a simple reflection around that point pi r. In terms of the circle, it's a reflection around these points. Okay, so we have one parity operation which reflects around the origin, and we have another parity operation which reflects around the point pi r. Okay, so now we're going to take our fields and write them as representations. By the way, we can now think of this quantity as being equal to S1 over Z2 cross Z2 prime if we have the Wilson line. The Z2 prime is the P prime. We have the P and the P prime, and so we can think of taking the circle and modding by Z2 cross Z2 prime, and in fact there was some confusion in the literature of what was going on. And what was going on is when you introduce the Wilson line, you can make an S1 over Z2 into an S1 over Z2 cross Z2 prime. Okay. Question?
So again, you're looking at a special subcase where the translation generated T is just the identity. At least you could have had a more general.
I did. I did. No, that's up there. Did you just come in? So T is the Wilson line.
Yeah, it's a minus 1, but still it's special.
Oh, yeah, no. You're absolutely right. You're absolutely right. It turns out, and I don't want to go into the detail here, if you're compactifying the theory on a circle, okay, your Wilson line can be an element of Zn. Okay, you can have an arbitrary Wilson line, more or less. But if you orbifold that circle, then you're stuck with having a discrete Wilson line. And t squared has to be equal to t has to be equal to plus or minus 1 eigenvalues. So it's the orbifolding which forces you to this discrete Wilson line.
So the fact that the P and the T commute, the fact that they can be simultaneously diagonalized is not an assumption.
I think that's an assumption. I'm assuming that they can be simultaneously diagonalized here.
But it doesn't need to be.
It doesn't need to be, and that would be more general. I'm not going to go into that. Okay, that's what you're talking. Absolutely. Go. Yeah, go. It's a Z2 prime. Well, yeah, no, it's a Z2. It's a translation. I'm not sure. You're confusing me now because when you say the Z2 torsion, what are you talking? That's right. On a circle, you can have more general thing. And if you look at this paper that we wrote with Nandi and Dermashek, we wrote down compactification on a circle and the general discussion of a Wilson line in SO3 on a circle, and then T is more general. It can have arbitrary parameter, and in that you would call a continuous Wilson line. Okay? And in fact, if you do compactification on, and I didn't want to go into that here. If you do compactification on a circle and you introduce a continuous Wilson line, then you'll find out that you'll break the gauge symmetry. You can break the gauge symmetry with the T, okay? And you can break the gauge symmetry where your W plus and W minus gauge bosons have an arbitrary mass with a continuous Wilson line. But when you do the orbifolding, you're stuck to a fixed mass for the W plus and W minus, which I'll do now, to be of order 1 over R. It's coming from the Z2, yeah. Yeah, yes, absolutely. Okay, so we're going to take our fields now and assume that they have the following parity operations. Parity acting on phi, and I'll just write down the y component of the field, takes us into phi of minus y, which is equal to p phi of y, where p can be the plus or minus 1. And then we'll have p prime on phi of y, can take us into phi of minus y plus 2 pi r, which will be equal to a parity p prime times phi of y. So we have these two possibilities: a parity operation around the point 0 or a parity operation around the point pi r. If we do that, then our mode expansion looks like the following. If I remember correctly, in the paper by Hall and Moriyama and somebody else who I can't remember, they discussed the case where the t doesn't commute with the p. So we can have parity eigenvalues here, states with p prime equal to plus or minus or plus or minus. And so we have 4 possibilities for the parities: plus plus, plus minus, minus plus, and minus minus. And in fact, our wave functions in the extra dimension, this one extra dimension, will differ depending on whether it's plus plus, plus minus, minus plus, or minus minus. So these are the components or the Fourier decomposition in the particular cases where it satisfies the different boundary conditions. The plus plus boundary condition, the plus minus. So these are functions of y. All of them are functions of y. And this is going to be proportional to cosine my over r. That'll satisfy positive boundary conditions under the first p, or positive boundary conditions under the second p prime. This one is positive under the first parity operation, y goes to minus y, but it's negative under the second parity operation. This is vice versa. And finally, okay, so these are the Fourier decomposition for the 4 possible states which satisfy these boundary conditions. I should point out the following thing, that any one which is positive under the boundary condition, the wave function in the 5th direction does not vanish on that boundary. So at the 0 boundary, these fields have non-zero wave function. These fields have 0 wave function. On the pi r boundary, these fields have non-zero wave function, but these fields vanish at the pi r boundary. Okay? So the pi r boundary and the 0 boundary are totally different. They're called, we'll think of them in a minute, once we do the SO3 gauge theory, as different branes which have different boundary conditions. I should also point out that the Kaluza-Klein masses of these states for the plus plus boundary conditions look like m squared over r squared, where m can be 0, and so this can have a massless mode. The plus minus and the minus plus have Kaluza-Klein excitations which are split off by half an integer. And the minus modes have Kaluza-Klein excitations where m goes, yeah. And I'm writing down mass squared. I could write down mass if I wanted to. Okay, this one has no massless modes because m starts out with 0 and goes up to infinity. So these modes are described by m. The integer m is greater than 0, greater than or equal to 0, and an integer. So I guess you would write that as a positive whatever integer. Okay, so these are the Kaluza-Klein excitations of the theory, and now we want to understand how we would use this symmetry to break the gauge symmetry, how we would use these boundary conditions to break the gauge symmetry. Okay, so let's look at SO3 again. And let's take a particular case of a Wilson line. We'll take t to be equal to the exponential of I pi T3, where T3 is the generator in the adjoint representation. So it's a 3 by 3 matrix in the third component only. It's a saying that essentially A5 got a vacuum expectation value in the third direction. Only the third component got a vacuum expectation value, and we pull out a T3. And in fact, if we do that integral from 0 to 2 pi r, what we're assuming there is A5 getting a vacuum expectation value, which is 1 over 2 pi r. 1 over 2r, excuse me. And I was worried when I started thinking about this, how can that be invariant under the orbifolding, the parity operation? A5, in fact, we'll choose A5 to go to minus A5. Let me, first of all, before I do that, before I get into bogged down with that, let me say the following. Let's choose certain parities for the fields. So let's look at the four-dimensional gauge fields, A mu. And we'll look at them, say, in the third direction. Okay? First of all, we have to assign this parity operation. What happens when A mu of y goes to A mu of minus y? Okay? Well, A mu appears in this field strength. All the A mu's appear in the field strength d mu A nu minus d nu A mu under y goes to minus y. What I want to argue is that A mu has to be even. It can't be odd. Remember, this has to be a symmetry of the theory. The parity operation has to be a symmetry of the theory so we can project out states. If A mu under y goes to minus y was odd, then these two terms would change sign, but this term wouldn't change sign. And so the field strength would not transform invariantly or covariantly under this parity operation. So we have to choose A mu under the first parity operation to be plus. What about A5? Well, A5 appears in this field strength. Under the parity operation, d mu doesn't change, right? But d5 changes sign under y goes to minus y. This doesn't change sign under y goes to minus y, so therefore this has to change sign under y goes to minus y, so that the whole thing will be odd under the parity operation. And since the action includes f mu 5 squared, the Lagrangian is invariant under that parity operation. So we conclude that these states have to be odd under the first parity operation, so that this will be a symmetry of the theory. And we can project out by a symmetry of the theory. Okay, but we have the freedom now, and we've chosen that freedom by choosing this. We know what the transformation is for these fields under the second parity operation. A mu prime goes to T AM T, because that's how it transforms U. Well, let me first, it's a true statement, but let me make it clear. You can work out what this T is, the matrix structure of this T. The matrix structure of this T is -1, -1, +1. It's real. It has eigenvalues -1, -1, or +1. Just work out what T3 is. The way you do that is you do a Taylor series expansion of this, and you'll find that this is true. So T3, this quantity transforms in the following way, acting on the fields 1, 2, or 3. And therefore, since it's real, the transformation of the gauge field was UAM U dagger. Okay, so this is how the fields transform under the second parity operation. It's an element of the gauge group. Remember, it has to act on the field as an element of the gauge group in the particular representation of the field. These fields are in the adjoint representation, and so they transform in this way. And so this is how the fields transform under the second parity operation. But the second parity operation, I remind you, is not just the translation. It's P times T, or P prime. Or we can write this P as just simple parity operation there. Okay? So for these fields here, for A3, there's no question what happens. For A3, what happens is that we get plus. For A1 and 2, if I define the following quantities, if I define W mu plus or minus is equal to 1 over root 2 T1 plus I T2, and I ask what is T W mu, or, well, W mu plus or minus, excuse me, is not this. I'm trying to go too fast. W mu 1 minus or plus I W mu 2, and that multiplies T plus or minus equals T1 plus or minus I T2. Okay, so we break it up into plus, positive, and negative guys. Then the transformation T plus minus T gives you plus or minus T plus minus. Okay, and this is W1 plus minus or plus I W2. I'm sorry. You're right. You take the first, just like the W plus and W minus, you take the 1 and 2 components and make it into charge components with definite charge. If you look at A53, remember, has parity minus under the first thing, but under the second thing, again, this commutes with T, the Wilson line, and so this quantity just gets its parity from P, parity odd. However, if you look at W mu, plus or minus, or W5 plus or minus, you'll find out that these have parity plus and minus, and this has parity minus and plus. Okay, so I won't try to work it out because I'll confuse myself, but you can work it out for homework, and you see that we've broken up the theory so that the different gauge bosons have different parities. You notice that the only gauge boson which has a massless mode is A mu 3. All the other modes are massive. And so we've broken SO3 down to SO2 or U1. So this orbifolding folding is broken SO3 down to a SO2 or U1 subgroup, where the only massless modes is carried by this. These guys get mass. The lightest one has mass 1 over 2r. Okay? And so we've given mass to the gauge bosons, which are in SO3 divided by SO2. We've given mass to them at the compactification scale at amount this much. And we have a whole clues of Klein excitations of these states. I want to point out one more thing, is that the gauge transformation of the fields, the infinitesimal gauge transformation of the fields, has to be consistent with the boundary conditions. So for example, A mu 3 has plus plus boundary conditions. Under a gauge transformation, it transforms like this. This is plus plus boundary conditions, so this quantity here must also be plus plus. It's an expansion. The theta parameter is an expansion in x and y, and so you expand it out in y modes, and it has to be expanded only in plus plus modes. Okay? The A12 modes are plus minus, and so therefore, under an infinitesimal transformation, they have to be expanded in terms of theta 1 and 2. Transformation parameters have to be written in terms of plus minus modes. And these plus minus modes vanish at the pi r fixed point. And so what we can say is that we have a theory where in the bulk we have an SO3 gauge theory. All the fields that live have non-zero wave functions on the zero brane or zero fixed point, have plus wave functions which don't vanish on that brane. So we can call this an SO3 brane because we preserve the SO3 symmetry. We preserve the SO3 symmetry. It's a local symmetry on that zero brane. However, on the pi r brane, we've broken it down to SO2. We only have an SO2 symmetry on the pi r brane because all the transformation parameters vanish at this point. So we have SO3 in the bulk, an SO3 brane on the left side, and an SO2 brane on the right-hand side. Okay. So in the last 15 minutes, let me do an SU5 orbifold gut. And this is from a paper that I took from Hole and Nomura. It's probably one of the first, it's referenced in the notes. It's probably one of the first orbifold gut that they had written down. The initial idea for orbifold guts field theories was in supersymmetry was written down by Kawamura. And then Hole and Nomura did lots of model building. So what I'm going to do now should be pretty easy to understand. I'm introducing now SU5 and supersymmetry. So I'm putting the fermions back into the theory. We're compactifying on M4 cross, as they wrote it down, as Z2 cross Z2 prime orbifolding. We start out with the gauge sector of a superfield in 5 dimensions. The 5-dimensional gauge sector contains a field AM, which is in the adjoint representation of SU5. It contains a lambda and a lambda prime, which are 2 4-component spinners, well, I'm writing it down now in terms of 2-component Weyl spinners. There are 2 Weyl spinners under the, which are adjoint representations of SU5, and a field sigma, which is also a scalar, which is also an adjoint representation of SU5. This 5-dimensional gauge field can be thought of as coming out of 2. So this has an n equal to 1 SUSY in 5D. It can be thought of as coming out of a theory with an n equal to 2 supersymmetry in 4D. In other words, if I do dimensional reduction, I'm going to get something which looks like an n equal to 2 supersymmetry in 4D, which I'll write in terms of n equal to 1 supersymmetric language. So hopefully that's not too confusing. So let me say it one more time. We'll start out with n equal to 1 in SUSY in 5D. We'll rewrite it in terms of n equal to 1 SUSY in 4D. But we'll see that it looks like it has an effective n equal to 2 supersymmetry. In fact, it does. So this is the gauge multiplet in 4D. It contains the gauge field A mu. This is M. In 4D, we contain the gauge field A mu and a gaugino. And then we have a chiral, and this is the adjoint representation of the group. And we also have a chiral field, which contains a scalar, a complex scalar in the adjoint representation of the group, which is made up of this real scalar in the adjoint representation plus IA5 over root 2, and then a fermion, a Weyl fermion lambda prime in the adjoint representation of the group. So out of this 5D adjoint multiplet, we get a V 4D n equal to 1 supersymmetric gauge multiplet and a 4D n equal to 1 chiral multiplet, okay, which lifted back to 5D gives us n equal to 1 SUSY. And this quantity here can be thought of as the gauge multiplet. The two of them together is the gauge multiplet for an n equal to 2 supersymmetry in 4D. Okay. We're going to put these fields in our bulk. Okay, so we're going to start out with a bulk gauge theory. And let me tell you in advance what we're going to do. We have SU5 in the bulk. We have V and sigma that are bulk gauge fields, and we're also going to put our Higgses in the bulk. So I have to write down the Higgses. The Higgses in this theory, there are 2 multiplets, which I'll write down like this as H5 and H5C. This is n equal to 1 4D language. There's an H5 chiral multiplet in the 5-dimensional representation of SU5, and the conjugate multiplet, or 5 bar, of SU5. Together, this forms an n equal to 1 5D multiplet. In the effective 4D theory, this is an n equal to 2 hypermultiplet. Okay? And we also introduce something called H bar, which is H5 bar with a bar on it, and H5 bar C, the charge conjugate of that. So those are the Higgses in our 5D theory, and we put those in the bulk as well. Let's write it like this, simplified notation. Okay, so all of these states go in the bulk. And now we want to do orbifolding of this theory. And to make a long story short, I'm going to just give you the result. We take, first of all, we'll distinguish, we want it with the supersymmetry, what Kawamura showed is that you can break n equal to 2, the effective n equal to 2 supersymmetry down to an n equal to 1 supersymmetry by giving these fields and these fields different parities under the first parity operation. So in fact, we'll take these fields to be even under the first parity operation and these fields to be odd under the first parity operation. Okay? If we do that, and you can show that that's a symmetry of the theory, and that's what I don't have time to do, but you can show that that would be a symmetry of the theory to choose different parities for these fields, and we'll take these fields to have these boundary conditions. So at the massless level, we only get an n equal to 1 supersymmetry in 4D. with those boundary conditions. So we break the effective n equal to 2 supersymmetry down to an n equal to 1 supersymmetry. We'll also give this positive boundary conditions and this positive boundary conditions under the first parity operation. So that's the first parity operation. The second parity, and this would have negative boundary conditions, and this would have negative boundary condition under the first parity operation. Okay? If we do that, we only preserve the H5s and H5 bars in the low energy theory, but we haven't said if they're massless modes or not. We have to choose the second parity operation. Okay? The second parity operation will look something like this. First of all, the first parity operation, I told you how it acts on the different multiplets. On the SU5 gauge degrees of freedom, this is the way it acts. In other words, it doesn't do anything on the SU5 gauge degrees of freedom. So we preserve the SU5 on this boundary. And so we call this an SU5 brane. On that boundary, the SU5 symmetry is not broken. The second parity operation, P prime, in terms of SU5 quantum numbers, does this. So this is a diagonal. This is the diagonal of the 5 by 5 matrix. It's minus, 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 plus, plus, almost like what we had for SO3. This actually will break SU5 down to the standard model. The gauge fields in the standard model, well, we break it down to the standard model. So let me just write down now the table that I need to write down. The table of quantum numbers under the two parity operations for all the fields. So we have under SU3 cross SU2 cross U1, the vector fields in the octet representation of SU3, the singlet representation of SU2, and with zero hypercharge, those are plus plus modes. The sigma fields, which are octets, singlets, and zero, are minus minus modes. Okay? So we'll get massless gauge bosons in SU3. Similarly, the SU2 triplet gauge bosons are massless. These guys are massive. And the hypercharged gauge boson is massless, or it contains a massless mode, and its corresponding chiral partner is massive. The ones which are in SU5 over SU3, in other words, the ones which mediate proton decay, are massive, so they get mass at the compactification scale, and their chiral partners have those quantum numbers. And similarly, the conjugate of these guys have the same boundary conditions. If we look at the Higgses, we have the following parity operations, or boundary conditions for the Higgses. So the Higgses break up into a Higgs 5, breaks up into a triplet under SU3 with quantum numbers 3, 1, and minus 2/3, and a doublet, which we called H, 1, 2, and plus 1, hypercharge. This is plus minus, this is plus plus. The conjugate TC 3 bar 1 2/3 is minus plus, and this guy here, HC 1 2 minus 1 is minus minus, and similarly T bar 3 bar 1 2/3 is plus minus. The Higgs bar 1 2, the one that couples the down quarks, is plus plus, and T bar C 3 1 minus 2/3 is minus plus, and H bar C 1 2 plus 1 is minus minus. So the bottom line is the following. If you ask where are the massless states of the theory, the massless states are up here. We have an SU3 cross SU2 cross U1 gauge sector, which remains massless. And we have a pair of Higgs doublets, which remain massless. We've done doublet triplets splitting. The color triplet Higgses get mass at the compactification scale. And the X and Y gauge bosons, which are in SU5 and not in SU321, get mass at the compactification scale. On this brane, we have all the multiplets in a complete SU5 representation are non-zero, so we have an SU5 brane, but the only symmetry at this brane is the standard model. Okay? And now the only question is what do we get for proton decay in this theory and gauge coupling unification? And I got 5 minutes to discuss that. Question? Up there? Second line? 130? Is that what you're talking about? No, it's a triplet under SU2. This is the gauge bosons, which are the SU2 gauge bosons, which are triplets. There are 3 of them. Okay. So what I want to discuss is there's lots of things you can discuss. I'll just discuss now, and you can look at my notes for other things. Gauge coupling, unification, and proton decay. You see now we've done gut symmetry breaking by orbifolding. So we didn't have to put in a Higgs sector of the theory to do gut symmetry breaking. We've done doublet triplet splitting by orbifolding. So we didn't have to put in a horrible gauge sector or Higgs sector which does that. You'll see that, in fact, if you ask where this might come from string theory, this is perfectly natural in string theory. In fact, orbifolding was discussed in string theory about 10 years before it was discussed in this language in field theory. So people were doing orbifolding and doing doublet triplet splitting already, and breaking the gauge symmetry already in string theory by orbifolding, and also getting chiral theories by orbifolding. So all this was known in string theory, and we're just applying it to field theory and seeing what we can do phenomenologically. So it's sort of a bottom-up, top-down approach. Okay, gauge coupling unification. We have corrections up until we get, so we have 2 scales in the theory. We have a weak scale, mz, and we have a compactification scale, mc, which is 1 over r. Say 1 over r, 1 over 2r, depends what you call it. And in this theory, we have to put in a cutoff. So we'll call m star the cutoff. There is no gut scale here. There is no, the 4D gut scale doesn't make any sense at all in this theory, okay? From here to here, we can do the renormalization group running with just the massless states of the MSSM. Below this scale, we have to include all the, well, here is the standard model, SU3 cross U1 electromagnetism. Here is the MSSM. And we have all the massless modes of the MSSM. And once we get here, we have all these Kaluza-Klein excitations. So we still get, in principle, threshold corrections to our renormalization group running once we get above this compactification scale. And it's at this scale here that we've defined the theory. We've defined the theory at this cutoff scale, and that's where the gauge couplings unify. And so we have to write down, I'm going to just write down the result now because of lack of time. You can look at the first paper that I'm familiar with that looks at this, integrating out the Kaluza-Klein modes and see what's the effect on gauge coupling unification, is a paper by Dinas, Dudas, and Gergeda. And then was followed by other papers by Hall and Nomura, and then a very nice paper by Contino, Ratazzi, and Pilo. Anyway, it's all in my notes. But so the relationship between the gauge couplings at the weak scale and the gauge coupling at the cutoff scale is given by this formula, minus BI MSSM over 2 pi log M cutoff divided by MZ. This is coming from integrating up the massless modes of the MSSM all the way up to the cutoff scale, plus 1 over 4 pi BI plus BI minus minus. You just take the general formulas for B's that I've written in the notes explicitly, but here you're only including the massive Kaluza-Klein modes which have plus or minus boundary conditions. The ones with plus minus don't contribute to a logarithmic running, in fact. That was the nice thing shown in these papers. By the way, the Dudas and Gergetta paper compactified on a circle. It was then Hall and Nomura who showed how to compactify on an orbifold and what you get that's changed. And this formula comes out of papers, either a paper by Contino, Ratazzi, and Pilo, or Pilo and Ratazzi, PQ. Anyway, this is the contribution of the Kaluza-Klein modes to logarithmic running. This should be the compactification scale. That's why it's Kaluza-Klein modes. And then there's an extra piece, which is B over 2 pi M star over M compactification minus 1. And this is a linear running. It goes like no logarithm here. Because remember, the effective gauge coupling in the 5-dimensional theory is massive. 1 over g squared has dimensions of mass. And so it runs, once you get above the Kaluza-Klein scale, you get a linear running to that gauge coupling constant. I should remark, no, I won't remark that here because I have no time. Now, I didn't include in here, but I should include in here delta I2, the correction due to 2-loop running from the weak scale up to the compactification scale or to the Z scale, plus delta I, the light threshold corrections. So this looks very much like what we had before in 4D theory, except there's no MGUT here. MGUT is not a physical quantity in this analysis. But you can make a mathematical identification of this formula to the formula I wrote down in the 4D theory, okay, where you get the following identities. In 4D, we had a quantity which we called alpha gut to the minus 1, which was the value of the gauge coupling at the gut scale. In our 5D theory, and if I look at the expressions in both cases, this is equivalent to, in the 5D theory, to alpha star of minus 1 minus bg over 2 pi m star over mc minus 1. So there's a rescaling of the coupling constant from what this gut coupling constant is by this linear term, because once you get above the Kaluza-Klein scale, it's really in a 5-dimensional theory. I discussed the heavy threshold corrections in a 4D theory, and I showed you they have to be a certain size in order to fit the low energy data. In the 5D theory, this is replaced by 1 over 4 pi bi plus bi minus log of m star over mc. So you get threshold corrections. The heavy threshold corrections are now coming from the KK modes. And then to make a precise analysis, you still get this piece from the MSSM to really equate those two things, integrating from m star to m gut. Because in the MSSM, you only integrated up to m gut. And now you're integrating up to the cutoff scale. And so those are the corrections. So if you know how big this has to be, you can say something about this. Okay, so let me do that. Okay, I've gone over. If I evaluate this quantity delta SH heavy, in other words, this is the quantity which is 7/5 times delta 1 minus 12/5 times 12/5? I don't remember. Yeah, 7/5 times delta 1 minus 12/5 times, no, it's 7. Forget about what I'm saying. It's 5, I'm not going to try to remember. You remember there's a linear combination delta 1, delta 2, and delta 3 heavy, which is called delta S, which comes into the threshold corrections. This is the quantity has to be equal to 12 over 28 pi log. Now it's related to this. On the right-hand side, this quantity here, which had to be equal to 0.94, is equal to this thing on the right-hand side. In fact, the contribution of this BI MSSM just drops out when you define delta S, heavy. And so what you see is that 0.94 determines the ratio of the cutoff scale to the compactification scale. And in this theory, you find out that that has to be a factor of 1,000. Well, I'm over time. Should I stop now? Okay, I can finish up in questions later. Yeah.